Okay, in a previous video we examined the reactions of the tricarboxylic acid cycle, and now we need to look at the regulation of cycle activity. Regulation occurs at several different steps, and the first step we're going to investigate is the pyruvate dehydrogenase enzyme. Now this enzyme is not actually part of the TCA cycle. This is the step in between glycolysis and the TCA cycle. And this enzyme is responsible, of course, for converting pyruvate into acetyl-CoA. The acetyl-CoA then can be introduced into the TCA cycle by a condensation reaction with oxaloacetate. Now this enzyme, pyruvate dehydrogenase, is an excellent point for regulation because it is involved in a very important reaction generating acetyl-CoA. And in skeletal muscle, what we are going to see is that the regulation of this enzyme is just simply going to be slowing the amount of substrate flowing into the TCA cycle. This is going to regulate the TCA cycle by limiting the amount of acetyl-CoA substrate entering the cycle and slowing the process down if we are in a high energy state. So this particular enzyme is going to be decreased in activity when energy levels are high. Now this makes sense because we want to slow the process down in skeletal muscle in order to control the amount of substrate moving through the oxidative pathways. Now when we turn our attention to the liver, hepatocytes, this is going to be an even more important reaction because this will allow us to take pyruvate in the liver, and instead of producing acetyl-CoA when energy levels are high, we will be able to convert the pyruvate into oxaloacetate and then on to gluconeogenesis. But we'll get there when we talk about the liver. So how is PDH regulated? Well, recall that there are three subunits to the PDH enzyme. These consist of E1, E2, and E3. Remember, the thymine cofactor associates with E1 and mediates the decarboxylation reaction to place an acetyl group on the pyruvate, from the pyruvate into the complex itself. E2 has the lipoate functional group, and this will be transferring the group from the thymine residue onto the lipoate for further processing and generation of acetyl-CoA. Finally, E3 has our flavin adenine dinucleotide cofactor, which will perform the redox reaction to regenerate the lipoate to continue the enzyme. Now, under conditions of low energy state, we can assume that this enzyme is in an active state. Active means it is continually processing pyruvate into acetyl-CoA. Now, in order to regulate this enzyme, we are going to call on an accessory enzyme. And what this accessory enzyme is going to do is it's going to convert the pyruvate dehydrogenase complex into an inactive state. This particular regulatory enzyme is called the pyruvate dehydrogenase kinase. So this is an associated regulatory subunit that is going to be taking ATP and using the energy of ATP to phosphorylate the E1 complex. When the E1 subunit is phosphorylated, it becomes inactive. The kinase is actually able to perform multiple phosphorylation reactions to ensure proper regulation of the pyruvate dehydrogenase complex. Now then, the question is when would you want this regulated? When would you want the complex of PDH to be inactivated? Well, for example, when the energy levels are high. Now, because we are in the cytoplasm, in the mitochondrial matrix, the most important energy molecule that we are going to have is NADH. Recall that the job of the TCA cycle is to generate lots of NADH. So as our energy levels rise, the NADH concentration begins to increase because we are generating more energy. This will stimulate the kinase activity of PDH. By activating the kinase, we will increase the phosphorylation of the E1 subunit and inactivate the enzyme. The other factor that will increase the kinase activity is the concentration of acetyl-CoA. So naturally, as the concentration of acetyl-CoA increases, which means that the PDH activity is high, this is going to be entering the TCA cycle to generate more NADH. So this essentially will also regulate by stimulating the kinase activity, and in doing so, slow the activity down by phosphorylating the E1 subunit. Now, when we reverse the process, for example, when NADH levels begin to decrease, that means that we will have an increased concentration of NAD, the oxidized form. This increase in NAD will inhibit the kinase activity. By inhibiting the kinase activity, we can reduce the phosphorylation of E1 and slow the inactivation of the dehydrogenase complex. Likewise, as the enzyme is slowed because of the kinase, our acetyl-CoA levels will begin to drop. That means that pyruvate, the substrate, will increase its concentration. Pyruvate, increased concentration, will also serve to inhibit the kinase activity, therefore leaving the dehydrogenase complex more in an active state. Now then, the question becomes, once you have phosphorylation on the E1 subunit, what removes the phosphate in order to reactivate the enzyme? Because the phosphate must be removed as inorganic phosphate. This is done by the pyruvate dehydrogenase phosphatase regulatory subunit. So again, the phosphatase is a counterenzyme to the kinase. Kinases place phosphate groups on subunits. Phosphatases remove them as inorganic phosphate. Now, this enzyme has a basal activity level, so that whenever it sees a phosphate group, it's going to hydrolyze that phosphate off and reactivate the enzyme. But in skeletal muscle, we want to make sure that we can stimulate this activity. So what's going to stimulate this is an increased concentration of calcium. So calcium will activate the phosphatase enzyme. This makes sense because increased calcium concentrations are required for muscle contraction. Muscle contraction requires ATP. So as our use of ATP increases because of muscle contraction, which is stimulated by calcium, we want to make sure that the energy-producing pathway is jump-started. So calcium is a signal for muscle contraction, which is going to be using ATP. That calcium also stimulates the phosphatase activity to reactivate the pyruvate dehydrogenase complex by activating the phosphatase, dephosphorylating the E1 subunit, and now the enzyme is ready to convert more pyruvate into acetyl-CoA to put into the TCA cycle. The next step of regulation of the TCA cycle is with the enzyme isocitrate dehydrogenase. So now, this step here, we are actually in the TCA cycle. So recall, this particular enzyme converts isocitrate into alpha ketoglutarate. Now, because this is a dehydrogenase reaction, this is a redox reaction, we are going to be oxidizing isocitrate, and so therefore we need something to move these electrons to. So this is one of our NADH producing steps. So as we will see with most dehydrogenase enzymes, the concentration of NADH is going to be controlling the activity of the dehydrogenase enzyme. So as the NADH levels begin to rise, this also means that the limited supply of NAD is beginning to decrease. So the NADH, under these conditions, will be an inhibitor of the dehydrogenase. So again, as our energy levels rise, we want to slow the cycle down. So we see that NADH is controlling PDH activity back here, but it's also controlling enzymes within the TCA cycle itself. NADH is the proper regulator, the most effective regulator, because this is the energy-carrying molecule in the matrix of the mitochondria. The next step of regulation is the enzyme alpha-ketoglutarate dehydrogenase. This is the next step in the TCA cycle from isocitrate dehydrogenase, and this enzyme is converting alpha-ketoglutarate to succinyl-CoA. Now recall, this enzyme is very similar in structure to the pyruvate dehydrogenase enzyme, in that it requires thymine, lipoate, and FAD to perform this reaction. This being a dehydrogenase, it is also going to need a redox partner, in this case, again, NAD, to form NADH. As we saw with the isocitrate dehydrogenase, as our NADH levels begin to rise because our energy charge is high, our NAD levels begin to drop. So the necessary cofactor to keep this enzyme going is becoming reduced, lowering its concentration. The reduced form of NAD, NADH, is now going to inhibit the alpha-ketoglutarate dehydrogenase. Very much the same as the isocitrate dehydrogenase. Now, as you can imagine, if you look forward in these reactions in the TCA cycle, we have one more point of regulation. And you can guess this one probably. This is the malate dehydrogenase. So you're beginning to see a theme here. Dehydrogenase enzymes are excellent points of regulation because they are producing the energy-generating molecules, NADH. Now in this case, this enzyme in the TCA cycle is converting malate to oxaloacetate. Again, this reaction is a redox reaction, so we are going to oxidize malate into oxaloacetate. So we need a partner to reduce, and that is going to be NAD to form NADH. And the same principle holds with this enzyme as the previous two. As energy charge begins to increase, NADH levels begin to rise, NAD levels begin to drop. This then becomes, as the previous two enzymes, an inhibitor. NADH levels become an inhibitor of malate dehydrogenase. Now, one point to note on this is that the forward reaction from malate to oxaloacetate, the standard free energy of this reaction is a positive 7.1. The previous two reactions, this reaction, standard free energy, is a negative 8.0, and this reaction, standard free energy, is a positive 1.5. So these reactions are moving forward because of the substrate-product relationship. As the TCA cycle is progressing, the product of this reaction is disappearing. Substrate continues to flow into the TCA cycle so that now the concentration of product over a concentration of substrate remains small. That gives us a negative free energy change to keep the cycle going. What about malate dehydrogenase? The standard free energy is a positive 7.1. This is extremely large and a very difficult barrier to overcome. If you look at this reaction carefully and think about it, the reverse reaction from oxaloacetate to malate is actually very favorable because its free energy change is negative 7.1. So the tendency of this enzyme is wanting to go backwards. But if we go backwards on this reaction, we cannot progress through the TCA cycle. We cannot come back to oxaloacetate to begin another round of the cycle. So this reaction, in spite of this high standard free energy change, needs to move in this direction. And the reason for this is the reason it does is because the oxaloacetate condenses very rapidly with acetyl-CoA to form citrate. So what this in essence means is that whenever oxaloacetate is formed from the redox reaction of malate, the oxidation of malate, it is going to be condensing with acetyl-CoA and disappearing into forming citrate. So this means that our product concentration of this reaction is going to be remaining near zero. And recall that our true free energy change is our standard free energy plus gas constant times temperature and the natural log of the concentration of product over the concentration of substrate. So this reaction is reflected in our thermodynamic calculation. Even though we have a large positive standard free energy change, our product of this reaction, oxaloacetate, remains near zero because of the condensation of acetyl-CoA. If this number, this quotient, remains near zero, the natural log of that will be a very large negative number, overwhelming the positive nature of this particular reaction in this direction, giving us a negative delta G to keep the malate dehydrogenase reaction continuing.